Okay, Chemistry 111. This is practice exam 4. You can see on the first page, I have the constants and formulas. You will be allowed to bring a sheet similar to this into the examination room on using Respondus Lockdown Browser. I will post that sheet to D2L so that you can print it out and have it in plenty of time. The sheet will look virtually the same as this one here. We have the Rydberg constant, we have Planck's constant, the speed of light, some formulas, and we have energy of light, we have the speed of light, we have the Rydberg equation, we have de Broglie wavelength shown here, and then we also have the periodic table, which you're going to use mostly for the second half of the exam, right? Anyhow, let's get started here and tackle some of the questions. Question number 1 says, which of the following wavelengths of electromagnetic radiation has the highest energy? We have all of these wavelengths here. Unfortunately, some of them are in nanometers and other ones are in meters. I'm going to go ahead and convert the first one into nanometers. Since I know that one nanometer is equal to 1 times 10 to the minus 9 meters, I know that A is actually equal to 3.50 nanometers. So I've got that one. So I've got A done. These two are good. E, again, I know that in 1 nanometer, I have 1 times 10 to the negative 9 meters, like that. I haven't worked this out, so let's see here. We have 8.4 times 10 to the negative 7. We divide that by 1 times 10 to the negative 9, and we get 840 nanometers. And then, so now we get that one. And then for the next one, we have 2.5 times 10 to the negative 5 divided by 1 times 10 to the negative 9. And we get, we'll just put this as 25,000 nanometers. So now we can compare all of these, right? We can compare all of these wavelengths because we have each one of them written down in nanometers. Now, what do we know about energy and wavelength? Well, if you look at the formulas that are given on the first page, we see that energy is equal to Planck's constant times the speed of light divided by wavelength. We also know that Planck's constant and the speed of light are constants. Therefore, right, we can rewrite that as energy is going to be directly related to the inverse of wavelength. So that means that the shorter the wavelength, the shortest wavelength of all of these is going to have the highest energy. And the reason why is because they are inversely proportional. If I look at all of these wavelengths, the shortest one of all of them is the 3.50 nanometers. And so the answer is A. Question number 2, we use this figure below, which has wavelength in nanometers, frequency in hertz, and it tells us what the type of radiation. Categorize electromagnetic radiation with an energy of 6.6 times 10 to the negative 16 joules per photon. Well, if we go back to that equation that we looked at a few seconds ago, energy is equal to hc over lambda. If I can calculate the wavelength from the energy in joules, I can if I can calculate the wavelength from the energy in joules, I can compare that to the number or the scale of the wavelength here. So let's rewrite this equation as wavelength is equal to hc over E. We have Planck's constant, which is 6.63 times 10 to the negative 34 Joule seconds times the speed of light, which is 3.00 times 10 to the power of 8 meters per second, divided by my energy, which is 6.6 times 10 to the negative 16 joules per photon. And again, a photon is just a bundle, package of, energy, or a package of light energy. And so when we punch all that spinach into our calculator, we get that our wavelength is equal to 3.0 times 10 to the negative 10 meters. But you can see that my scale for my wavelength is nanometers. And we know that in 1 nanometer, we have 1 times 10 to the minus 9 meters. When we work all that out, we see that meters cancel, and we're left over with our wavelength in nanometers, which is 3.0 times 10 to the minus 1 nanometers. And so that would fall in this range, which is closest to the X-rays. Question number 3. What's the wavelength of radiation that has a frequency of 5.39 times 10 to the 14 reciprocal seconds? And they've given us the speed of light. Well, we could round that off since our answers, well, no, a couple of them have 4. No, one of them has 4. No, it still only has 3 sig figs. So we only need 3 sig figs anyway. Why do we need all that, right? Well, we're going to use the formula that the speed of light is equal to wavelength times frequency. And we're going to solve for frequency, which is equal to speed of light over wavelength. I'm just going to put in 3.00 times 10 to the 8 meters per second and divide that by my wavelength, which is 5.39 times 10 to the power of 14 reciprocal seconds. You can see that seconds are going to cancel, and I end up with my wavelength in meters. And when I punch all that into my calculator, I get that my wavelength is equal to 5.56 times 10 to the negative 7 meters. That would be too easy. I have to convert that into nanometers, and I know that in 1 nanometer I have 10 to the negative 9 meters. In the interest of space, I'll just write it quickly like that, and I get that my, what am I doing here? Sorry, you guys, I made a mistake. I'm solving for wavelength. Sorry, I'm tired and I'm thinking of too many things at once here. So my wavelength is equal to speed of light over frequency, isn't it? Anyhow, nobody stopped me. I was just testing you. There we go. So we get that our wavelength is equal to 556 nanometers. Come on, nanometers. Is that one of the answers? Good. Okay, let me think a little more clearly about this one. It says calculate the frequency of visible light. Having this wavelength, right? We're going to use the same old equation that speed of light is equal to wavelength times frequency. We're going to solve for frequency, which is equal to c over lambda. We're going to put in our speed of light. We're going to divide that by our wavelength, which is 486 nanometers. Let's just write it like this: 486 times 10 to the minus 9 meters, like that. That works. So meters are going to cancel out. Remember that reciprocal seconds are equal to hertz. It's the same thing. And when I punch all that into my calculator, I get that my frequency is equal to 6.17 times 10 to the 14 hertz. Like that. Number 5, what's the minimum energy, or what is the energy in joules of 1 photon of X-ray radiation with this wavelength? Well, remember that we saw an equation a few minutes ago where we related energy and wavelength, and it was E is equal to hc over lambda. H and C are constants, and so if we have wavelength, we can calculate energy, can't we? And so let's use that formula, and we'll say that E is going to be equal to 6.63 times 10 to the negative 34 joules times seconds. That's Planck's constant times the speed of light, 3.00 times 10 to the 8th meters per second. And we're going to divide that by the wavelength, which is given in nanometers, but since we know that 1 nanometer is equal to 10 to the negative 9 meters, we can write that as 0.120 times 10 to the negative 9 meters. It just makes putting it in your calculator a lot faster than converting into nanometers. We see that meters and seconds cancel. We're left over with our energy with the units of joules, which is good. And we get that our energy of X-ray radiation with a wavelength of 0.12 nanometers is 1.66 times 10 to the negative 15 joules. So that's how much energy one photon of radiation with this wavelength has. All right, the next question deals with the Balmer series. It says the second line of the Balmer series occurs at a wavelength of 486.1 nanometers. What's the energy difference between the initial and final levels of the hydrogen atom in this emission process? Well, we know that E is equal to hc over r lambda. And so we can solve saying E is equal to h times c over our wavelength. Planck's constant, 6.63 times 10 to the negative 34 joules times seconds, multiplied by the speed of light, divided by my wavelength, 486.1 times 10 to the negative 9 meters. Double check our units. Looks good. And we get that our energy is equal to 4.09 times 10 to the negative 19 joules. Like that. Okay, let's try another one. Number 7, calculate the energy in joules required to excite a hydrogen atom by causing an electronic transition from the n is equal to 1 to the n is equal to 4 principal energy level. Recall that the energy levels of the hydrogen atom are given by this equation. Well, I would probably go with this equation here, since we're going from a high level to a low level. It's getting excited from n low is going to be equal to 1 to n high, which is going to be equal to 4. Okay, and it's asking us to solve for energy. And when we're solving for energy, this is the Rydberg constant that we use. If we were solving for 1 over lambda, then we would use that one, but we're solving for energy. And so let's get our formula all set up. E is going to be equal to RH times 1 over the n initial, or n low, I'll just call it n low squared, minus 1 over n high squared, like that. Okay, let's plug some numbers in. E is going to be equal to minus 2.18 times 10 to the negative 18 joules. Have 1 over 1 squared, that's where we start, so that's obviously 1, divided by 1 over 4 squared, so that's 1 over 16. Anyhow, and when you put all that in your calculator, you get that your, and I should have here delta E, my delta E, my change in energy is going to be equal to negative 2.18 times 10 to the negative 18 joules multiplied by 0.9375. And we get the change in energy. I mean, you could write it as delta E, you could write it as E. I mean, it's the amount of energy that's required for this transition. It's going to be equal to 2.04 times 10 to the minus 18 joules, like that. All right, so here's the amount of energy that is required. Next question is in a similar vein. Calculate the frequency of light emitted by a hydrogen atom during the transition of its electron from the n is equal to 4 to the n is equal to 1 principal energy level. And so to do this, why don't we solve for the energy? Why don't we use the same equation that we did the last time? We'll use the Rydberg equation and solve for energy. And then since we know that E is equal to h times nu, we can just solve for frequency, which is equal to E over Planck's constant like that. I think it's probably the easiest way to solve the problem. So let's plug in some numbers here. We have our energy, which is equal to h nu. It's going to be equal to the Rydberg constant. Or sorry, we can solve this whole thing for frequency, can't we? Because we have h nu, which is equal to the Rydberg constant times 1 over 4 squared, right? Because this is the n initial minus n final, like that. So we have that our frequency is going to be equal to negative 2.18 times 10 to the negative 18 joules, multiplied by 1 over 16, subtract 1, divided by 6.63 times 10 to the negative 34 joules times seconds. And joules cancel, and we're left over with our frequency. And so our frequency is equal to 3.08 times 10 to the 15 reciprocal seconds. This next one's kind of a tricky one. It says here that if a hydrogen atom and a helium atom have the same kinetic energy. So you have to know that kinetic energy is defined as 1/2 times m root mean square speed squared, like that. Okay? And I'm comparing a hydrogen atom, which has a mass equal to 1 gram per mole, right, approximately, and a helium atom, which has a mass of about 4 grams per mole. So if these two elements have, or these two atoms rather, have the same kinetic energy, what's the relationship of their wavelengths going to be? You know, you see that wavelength comes up in all of these. Well, the relationship between the wavelength is going to be as follows, and I don't really have a lot of space to solve here, but we know the de Broglie wavelength of something really small or something really big is given as such, that lambda is equal to Planck's constant over the mass times the velocity, okay, or root mean square speed. Okay, well, if I solve my KE, if I solve this equation for m times u, what do I get? Let's try it. It's kind of tricky to solve for this, but another way of rewriting that formula would be like this. If I know that my kinetic energy is equal to 1/2 times mv squared or mu squared, well, I could factor out the square from my mu, right? If I say KE is equal to 1/2, and then I factor out the square like this. Well, remember, in this expression, the only thing that's squared is the u, right? So now if I have the square on the outside, I have to multiply the whole dang thing by 1 over m, like that. But that enables me to isolate just this portion of it, right? So that means that my mu, which is what I'm looking for here, my mu is going to be equal to the square root of 2 times the kinetic energy times the mass. All right. Well, if I have that, then I could plug that into my equation right here, my de Broglie wavelength. And I could say that wavelength is equal to Planck's constant divided by square root of 2ke multiplied by m. Remember that when we compare these two atoms, Planck's constant isn't going to change. It's the same. And it tells you that they have the same kinetic energy. So kinetic energy cancels. So that means you can boil all this down to what? That wavelength is going to be directly proportional to 1 over the square root of the mass. Well, what are the atoms you're comparing? For my hydrogen atom, it's going to be equal to, or proportional to, I should say, 1 over the square root of 1, versus the wavelength of the helium is going to be proportional to 1 over the square root of 4. What's the square root of 4? It's 2. So that means that the helium wavelength is going to be half as long. Another way of phrasing that is that the wavelength of the hydrogen is going to be 2 times longer than the wavelength of the helium. Let's try another problem where we use the de Broglie wavelength equation. In an electron microscope, electrons are accelerated at great velocities. Calculate the wavelength of an electron traveling with a velocity. This is our u of 7.0 times 10 to the 3 kilometers per second. And we're also given our mass. Again, we're going to use de Broglie wavelength is equal to Planck's constant divided by mass times velocity. Remember that a joule is a kilogram meter squared per second squared. And so we're going to have to convert this mass into kilograms. Well, if I want to convert that mass into kilograms, we don't have a lot of space, but I know that 9.1 times 10 to the negative 28 grams. And I know that in 1 kilogram, I have 1,000 grams. And therefore, the mass in kilograms is going to be 9.1 times 10 to the minus 31 kilograms. So I've got that squared away. Well, with that in mind, let's plug some numbers into this equation. Our wavelength is going to be equal to Planck's constant 6.63 times 10 to the negative 34 joules times seconds divided by 9.1 times 10 to the negative 31 kilograms multiplied by 7.0 times 10 to the 6 meters per second. Again, if a joule is equal to a kilogram times meter squared per second squared, I'm not going to work all the units out here, but you can see how you end up with only the units of meters left over. And we get with a wavelength that is 1.0 times 10 to the negative 10 meters, like that. This is around the size of an electron, is around is around 10 to the negative 10 meters. And so our answer is D. Let's try a question that deals with electron configuration. It's asking us to determine the electron configuration for a lead atom. This is nothing more than just determining the electron configuration for lead. You can see that we're given the shorthand electron configuration for all of the possible answers, so let's just work with that. Okay, if we go over to the periodic table, we see that lead is found right here. It's element number 82. The noble gas that precedes it is xenon. And so we're going to start with xenon. What comes after xenon? Then we go to cesium and barium. So that means N is equal to 1, N is equal to 2, N is equal to 3, 4, 5, 6. So these are 6s2. Then we go to elements 57 to 71 down here. Remember that with the lanthanides and actinides, you take N and you subtract 2. So this is going to be 4f 14. Then we go to the Ds. We go from 72 up. So we have a total of 10 D electrons. So we're going to have 5D10. And then when we get into the 6Ps, we have 6P1 and 6P2. Just like that. And so this would be the electron configuration for our lead. All right. And if you compare these, you can see that the correct answer is this one right here, A. Next question asks us, which set of quantum numbers is not possible? We have our values of N, L, and ML, and MS. I'm going to throw this out there to my students. We know that N can be 1, 2, 3, so on and so forth. L can be 0, 1, 2, all the way up to N minus 1. ML is equal to negative L, all the way up to 0, all the way up to positive L. And then MS can be plus a half or minus a half. Is there any set of quantum numbers here that looks unreasonable to you? A, B, C, D, or E? I'll give you a hint. There's one of them that's messed up. Does anybody notice which one of these is off? I agree with you, Trevor. The answer is B. There's a big problem here, isn't there? When L is equal to 0, ML could only be 0, right? It can't be plus 1. So we'll put here ML cannot be 1. Okay? All right. The next question says, which of the following sets of quantum numbers represents an electron with the highest energy? Remember that we increase in energy as we go across the periodic table. As we go from one element to the next, we're increasing in energy. And so we have to figure out which set of quantum numbers represents the highest energy electron. Well, if we look at the first one, keeping in mind that when L is equal to 0, 1, 2, or 3, we have S, P, D, or F, and we know that energy increases going this way. The first one must be a 4S. The second one is a 4D. The next one is a 3D. The next one is a 5S. And the last one is a 4P. Well, if I compare all of these, the first one that I can eliminate is the 3D because it's lower in energy than all of them. If I compare a 4S, a 4D, and a 4P, well, based off of this trend right here, we know that the 4D is going to be higher in energy than those other two. So then it becomes, which one is it here? Is it the 4D or is it the 5S? Well, remember that energy depends both on N, the principal quantum number, and it depends on L, the type of orbital. if we go back to our periodic table and we compare those two, here we have n is equal to 1, 2, 3, 4, 5, and we're comparing a 5s, which would be here. These would be 5s electrons to here. This would be 4d. And since the 4d come after the 5s, they're going to be higher in energy. And so our answer will be B.